I was muted. So. Hi, Aaron. Hi,
Hello.
Henry.
Hi.
Hello.
Greetings from Australia.
Oh, yeah.
Greeting from Shanghai.
And of course, I'm in Singapore.
And let's get started. Today, we are very
Okay.
lucky to invite Aaron Tai to share his experiences and insights of using AI in his work. Before we get started the webinar, let me introduce him first. Aaron Tai is an academic librarian with over 15 years of experience in various areas of librarianship. He is currently the head of data services at Singapore Management University Libraries, where he oversees and leads a team of librarians providing research support in discovery, open access, and other emerging areas. Aaron has a keen interest and curiosity in information science and library science, and he shares his thoughts on his award-winning blog, Musings about Librarianship. He has also received several honors and awards, including the CALA Award from the Pacific Rim Research Libraries Alliance and the Library Association of Singapore Professional Services Award. He's active on Twitter and recently Blue Sky with the account at Aaron Tai. And after his talk, we'll leave you time for you to ask questions. Let's welcome Aaron.
Yeah, thank you, Henry. Let me share the slides first. Hope you can see the slides. Right, so yeah, thanks for having me. My name is Aaron. I'm from SMU in Singapore. And I'm going to talk about how AI and large language models are changing academic research. Okay, so I'm going to focus on one very particular aspect of AI literacy, right? AI literacy is a huge area. I'm focusing on how AI is impacting academic research. So my interest in GPT models started back in 2020. Back then, I actually started to play with GPT 3.0. This was before ChatGPT, which is GPT 3.5. And I was fortunate enough to be contacted by some of the earlier companies to try out tools like Elicit back in late 2021, early 2022, which were some of the first academic search engines to be enhanced with AI, more particularly large language models. And this led me down the whole rabbit hole. For the last 3 years, I've been really studying information retrieval techniques. And basically for this talk, I'm going to go a little deep about how AI search is different from, say, Boolean search and some of the pitfalls of some of these tools. So right now, there are two types of tools that librarians call AI search tools, right? The first type is what I like to call citation-based literature mapping tools, right? Things like ResearchRabbit, LitMaps, connected papers, right? I don't really consider this type of tools real AI, but I guess AI can be defined any way you want. I will spend like maybe 10 minutes talking about such tools before moving into the AI search tools that I think are of interest. So things like ResearchRabbit and connected papers, there are many different versions of them, but how they work tends to be similar, right? Typically, what you do is that you select one paper that's relevant, sometimes called the seed paper, you throw into the system, and the system will use some sort of algorithm, which is based on citations to suggest potentially relevant papers that you can add, right? And as you add more papers, you iterate and you get more and more relevant papers, right? Typically, such tools will include some sort of visualization, which may or may not be useful. The key point to note is that most of these tools do not use large language models. They do not use things like GPT models or BERT models, right? There are some exceptions, but the majority of them are just using citations to actually recommend papers. So for example, on the right, you can see connected papers. And essentially, the position of each circle represents a paper, and the position of each paper represents how close they are and how similar the papers are. But how is similar papers defined? So if you look at connected papers, they say that they calculate this similarity matrix, right? This number, which is based on the concepts of co-citation and bibliometric coupling, right? This sounds very scary, but basically what it means is that if a paper shares similar citations and or shares similar references, they are considered similar, right? There's a formula, but essentially you're just counting the overlap in terms of citations as well as references. So most of you are familiar with the idea of forward and backward citation, right? So if you have one paper that's relevant, see paper 1, right? You can look at, say, DEF, which is what it cites, which may be relevant, and you look at ABC, right, which cites it and may be relevant. So you can do this manually, right? But you can do other types of citation checking, right, which are more indirect. So for example, the idea of co-citations. So let's say you have paper 1, see paper 1 that's relevant, and it is cited by ABC, right? And it just happens that ABC also cites another paper. And this paper might be potentially relevant, right? Because they are cited, they are also cited by ABC, right? So this is technically called a co-citation, right? So the algorithms from connected papers will take this into account to consider similarity. Of course, you can do it in reverse, right? See paper 1, which is relevant, cites DEF, right? And you have another paper that also happens to cite DEF. So logically, it would imply that this other paper is potentially relevant, right? And the algorithm might suggest this paper as well, right? If you notice, right, this is a case where even though the potential relevant paper 3, they may have 0 citations, they may not be cited at all, but because they cite the same set of papers as a seed paper or relevant paper, it may still be suggested, right? So there are other types of ways to use citation networks to identify potentially relevant papers. But essentially, what actually happens is that when you for certain tools like ResearchRabbit, you can throw in multiple seed papers, and then it gets even more confusing, right? So you could say that like seed paper 1, 2, 3, they collectively cite DEF, GH, and then there's another paper that's potentially relevant that cites maybe DEF and G and so on, right? So there can be different algorithms. You don't have to match every single paper, right? But there are all these algorithms based on citation networks, right? So this is different from GPT type models, which actually generate text, right? This is just, so these tools are basically based on citations, right? There's a lot to say about these tools, but I don't want to focus too much. The main thing to know about such tools is that they are limited by the index they are using, right? So what index are they using to find all these papers, right? So typically tools today, they typically use a combination of things like Semantic Scholar, OpenLX, Lens, Crossref, right? These are very big and free sources of data, scholarly data. There are around 200 million records, which is a lot because Scopus itself is only 80 million. But it also means that they will have a lot of like, predatory papers. They are roughly at the size of Google Scholar, smaller than Google Scholar, but very large, right? Even though they are very large, there are still gaps, right? So as you try them, you'll notice, for example, they don't have citations for monographs. They may have issues with finding certain documents within humanities or law. For example, there's no case law, right? Besides the fact, so these tools are as good as their sources, right? And the other issue is not just the fact that the certain things may not be in the index, but the completeness and accuracy of the metadata of such tools are also questionable, right? So there are various papers that have studied how accurate and how complete the metadata is in Semantic Scholar versus say Scopus. And typically speaking, these tools, they're using indexes that are less complete and less accurate than Scopus or Web of Science. Right, so for example, there was a recent study that showed that a lot of OpenLX is actually missing out a lot of references to papers, right? Yeah. So I won't really go more into this, but I'll go on to the more exciting tools, in my opinion, tools that use so-called large language models or GPT type models, right? So just as there is Google and Google Scholar, there in the academic search world, just as there's Google and Google Scholar, right? For AI search, there are web-based kind of tools like Perplexity, Copilot, which are AI enhanced, but they search the whole web. And then there's academic type search engines that use AI, right? The very first one that I'm familiar with is Elicit.com. They were an early partner of OpenAI, and back then they were using an older GPT model, GPT 3.0, right? Their counterpart was Perplexity, which was working on web search, general web search, and Elicit was working on academic search. And Elicit actually uses the Semantic Scholar dataset, right? So you can go Semantic Scholar and search use that search engine to search, and this gives you an idea of what Elicit is searching over, right? And of course, by now, a lot of our legacy or existing academic databases and search engines have started to also do the same thing. They've started to add AI, right? So things like Scopus AI, Web of Science Research Assistant, Primo Research Assistant, Statista has a research assistant, so on and so forth. I've been predicting this for the last 2 years, but my guess is in a couple of years, almost every academic database that you are used to, there'll be some sort of AI search inside there. Right, so why are people so excited about using adding AI to search, right? So the idea is that right now, what we call large language models, which are, if you want technical, is actually a transformer-based neural net, right? They actually achieve near human level understanding and near human level in terms of generation, right? There's a lot of debate about whether these tools truly understand, but I'm a humble librarian, so I'll skip past all the philosophy and just focus on the empirical results, right? So there are all these tools out there, right? Many tools, right? I have this list on my blog that has like almost 50 such tools already, right? But I think it's important to take a step back and look at the major ways that this AI search is impacting, AI is impacting search, right? And there are actually, I would say, 3 ways, right? So if you look at all these tools, there are actually 3 ways, right? The first way, which I'm going to spend a lot of time, is that the AI search is now a lot better at finding relevant results, right? Through natural language understanding. And technically, some people call it semantic search, and it differs quite a bit from the keyword, lexical, or Boolean type of search that we librarians are familiar with. Right? If you want to go even more technical, they're using things called dense embeddings or learns fast embeddings versus BM25. I'll spend a lot of the time talking about this and the implications for librarians teaching such tools. The other type of thing that's even more flashy is that in the past, when you use search, it will just show you documents that might be relevant to your query. These days, it's able to extract the answer from the documents and provide you with citations to these documents, right? And the technical technique that's used is called retrieval augmented generation. It's a very simple concept, don't worry. I'll explain it. And there are more advanced techniques that use knowledge graphs on top of retrieval augmented generation. The third use of AI search that some tools do is that they are actually extracting data and summarizing it and putting it into a table, right? Like a synthesis matrix. I won't spend a lot of time on this because this is basically still using retrieval augmented generation. Okay, so let's talk about the first type of the thing about AI search on how it can get more relevant results. Right, the holy grail for information retrieval for all these years, for 2 decades, has been the ability to understand the meaning of the words. Right, not just matching individual words, but understand the meaning. Right, and the current type of search tools, you can tell that they are AI search because they will encourage you to search in natural language. Right, this is different from the normal way we librarians search. For our normal search engines will tell users to drop the stop words, just put in the keywords, right? For the current AI search tools, they will ask you to type in natural language. Do not drop the stop words, right? The main strength of such tools is that they are less affected by what technically people call the vocabulary mismatch problem, right? Again, sounds technical, but it basically means you may not know what the right keyword is. And the other potential of AI search is what people are calling agent-based search, right? Tools are emerging like Undermine, which can actually mimic the way we search, right? So we do iterative searching and so on and so forth. And I will cover this later. So to show the power of semantic search, sometimes it's not very clear that you're doing it because in many cases, when you use tools like Elicit or CiteSpace, which have semantic search, you may not notice because you may just search in normal keywords and it looks normal, right? But here's one case where keyword search cannot work. Does not work. So I was reading this tabloid paper, I won't tell you why, and this tabloid paper was referring to this study, right? This study on cancer risk based on your profession, right? And like many newspapers, they are quite irritating. They don't actually give you the title of the study, right? So I spent a lot of time trying to find the study. Eventually I did. I think I spent about half an hour on Google Scholar and I finally found the study, right? So one thing I realized is that I could have simply copy and pasted the first 2 paragraphs. So you can see the paragraph here, right, from the newspaper. So it just describes the study. It mentions the journal, right, but it doesn't mention the author name. It doesn't mention which issue, right? So if you throw this whole paragraph into things like Elicit and CiteSpace, stunningly, you'll find that for elicit, the very first result is the correct paper, right? While for citation-based, the fourth result is the correct paper. When you think about this, right, this is definitely not standard Boolean keyword searching, right? Because if you look at what you are entering in, right, they do not match the full text, right? They do not 100% match full text for sure, right? And this is written in the news from the newspaper, so it's different from the jargon and the words used in the journal. Yet the semantic search in both search engines said that, could figure out that this is the closest in meaning to the text I've entered. Right, so this is definitely not keyword searching. If you have actually tried JSTOR, and JSTOR has a beta, right? There are now two searches in beta. There's a keyword-based result, which is a typical keyword that you're used to, and then there's experimental results, right? The experimental results, if you read it, is basically it understands your query and provides more relevant results, right? Even if you do not use the exact words, right? So this is actually a semantic search, right? And I found anecdotally that when you search in natural language for the experimental search, you get better results. It's not just academic search engines. Google has already added this since 2019, right? So in 2019, they actually wrote a blog post called Understanding Searches Better Than Ever Before, and they talked about using BERT type models, which is a transformer type model, to improve search. Right, so they gave an example where you search like 2019 Brazil traveler to US need a visa. And they showed that using this new semantic search, it actually understands that what you're looking for is you're from Brazil traveling to the US and not the other way around. Right, so the main problem with keyword searching is that it tends to do they call it a bag of word approach. Right, they will throw away all the stop words and then they will just treat each word independently, not caring about the order. But the semantic search that we are talking about can actually understand what this tool means. So it understands it's Brazil to US, right? So the latest AI language model search is understanding the meaning, the order of the words. Very different from normal keyword searching. Right, here's another example in Google Scholar where it doesn't have semantic search. So if you search like how to find review papers, right? So you're looking for techniques to find review papers. And you look at Google Scholar, it's randomly matching the word papers here, reviews there. It doesn't understand that review papers is one concept and how to find is one concept, right? So the results are quite bad, right? It's randomly matching papers that have all these keywords. Of course, you can say that, well, you can put, quotes to say review papers and so on. But the semantic search, in semantic search, you don't even have to do that. If you throw this how to find review papers in illicit or citation-based, which have semantic search, you will see the results are a lot better. Okay. So one of the ways to tell whether you're using, because sometimes it isn't obvious that the search that you're using is doing some sort of semantic search. One way, not foolproof, but one relatively good way to tell whether you're using a semantic search type engine is to throw in a chunk of text. If you throw in a chunk of text and it gives you nothing, there's a high likelihood that it's still doing a keyword search. But if you throw in a chunk of text and it still gives you something, there's a strong indication that the system is using some form of semantic search. How does semantic search work, right? I guess there are a lot of people. Okay, before I even go to that, why do we even need this semantic search? Why can't we just use keyword alone? And you can read my slide, but basically as librarians, we are aware that the main problem is we do not know the right keywords, right? Or the same word can mean many things, right? And there's been a lot of attempts to solve this problem, right? Like do stemming, right? Or do query expansion, right? For example, you search for heart attack and it uses thesaurus to expand to the medical term for heart attacks, right? So there are all these attempts, but at the end of it, we are still looking at individual words and trying to figure out whether this word matches or not, right? So the current solution that does semantic search, and there are a lot of technical terms for it. You may see people call it neural search, vector search, embedding search, right? But they all basically use the same type of technology. They are using embedding type of searching, right? So what is an embedding? An embedding essentially is you represent a word by a series of numbers, right? So what you have is an embedding model, right? You throw in a word like apple, and you go through the embedding model, it will generate a series of numbers, right? It could be like 200 numbers, 300 numbers, 1,000 numbers, right? And the question is, of course, how do you assign the numbers. And typically what they do is that they use a neural net to learn to represent the words in terms of numbers, right? So I'll give you an example, right? So how would you, so imagine that, let's say you have 1,000 words that are fruits, okay? 1,000 words, starting from A to Z, right? And one way to do it is to say, okay, let's have, since you have 1,000 words, let's have 1,000 numbers. And then, like, for example, apple would be 1, 0, 0, 0, 0, 9,000 zeros. And then apricot would be 0, 1, and then 0, 0, 0, up to 1,000, right? So this is called one hot word embedding. Clearly, this isn't very efficient, right? Because you may go like, but maybe apples and apricots are kind of similar, and we want to express this similarity. So one way you could do it to say is that let's not have 1,000 numbers. Let's have, let's say, 10 numbers or 10 dimensions. And maybe like one of the numbers will represent size, one will represent sweetness, so on and so forth. And then the 10th one might represent, say, texture, right? So the idea here is that you want to squeeze the 1,000 words into, say, 10 numbers, right? And each number would represent a certain aspect or certain dimension, right? So in this case, you are actually having you're having the word apple to be represented by 10 numbers or 10 dimensions, right? So you can do it in the example I was talking about fruits, right? You can do it for all the words. Let's say you're creating a search engine that recognizes, say, 10,000 unique words, right? 10,000 word dictionary, and you want it to be represented by 200 numbers, right? 200 numbers, right? And here's an example, right? And you're going to fill in the numbers here, right? So how do you actually do it, right? You're not going to do it manually, okay? You're definitely not going to do it manually, right? So what you can do, one of the tricks that people have done for linguistics is the idea that a word is characterized by the company it keeps. In other words, right, if two words are very similar, they tend to be used in sentences that are very similar, right? Here's an example, right? So if you look at this sentence, I won the lottery today, and I feel something happy. Do you notice that very and extremely can both fit in, right? So this implies that when you create the embedding, the numbers, the very and extremely must be very close together. They must be very similar, right? So this is the idea, right? You can take a lot of text from the internet and throw it into the neural net, right? And then the neural net will try to guess what is the next word. If it's wrong, it will do some sort of correction, back propagation. And eventually, if you do it enough, you'll be very good at guessing what the next word should be. And that is how the embedding model is trained, right? So this embedding model is basically this, right? It's kind of technical, but all you have to know is that essentially it learns to predict the next word, right? And once you have done that properly, right, it works beautifully, right? So this is the first embedding, right, where you represent a word with multiple numbers that seems to work very well. This is almost 10 years ago by Google, called Word2Vec, right? And what happens is that if you actually so-called represent them in a 3D space, you can kind of squeeze them in a 3D space. You notice that the embedding seems to make sense, right? Like, for example, king and queen are parallel to man and woman, or walking and walked is parallel to swimming and swam. Or if you look at the capital and countries, they seem to be located in a similar fashion. And you can even do mathematics. You can say, give me the embedding for king, take away the man part, add a woman part, and you'll pop up queen, right? On the right is the Python code, but essentially what the embeddings have learned is that there's some meaning in the embeddings in the numbers, right? They actually make sense if you do this type of analogy types of maths, right? So a king who isn't a man but a woman would be queen, and when you do the maths, it actually does give you the embedding for queen, right? So it captures meaning, right? And you can do it at the sentence level, right? That's how we did it at the word level. You can do it at sentence level. I'm swimming across the river bank, pass it through an embedding model, you get a series of numbers, right? I won't go into how you actually do sentence embeddings, but essentially it's the average of the word embeddings, right? So you can do that. And now you are equipped to understand how this type of embedding or semantic search works, right? How it works is you take the query, you throw it through the encoder or basically the embedding model, right? And then you get an embedding, a query embedding. And then your document, you throw it through the same embedding model and you get another embedding. And then you can run something called a cosine similarity match, right? I won't go into the maths of it, but some of you may even know constant similarity. But essentially, you compare the two series of numbers and give a score as how close they are, right? This is semantic search, right? Basically, take a series of numbers that represent the query, take a series of numbers that represent the document, and then calculate how close they are together, right? This is called cosine similarity. In reality, of course, you do it in advance, right? So before you even search, you take the documents. Let's say you got 1 million documents. You convert it into embeddings, a series of numbers, and store it in a vector database, right? So when you run the search, the only thing that you need to actually do the embedding model for is the query itself, which is relatively fast because you only have one line, right? And then once you have this, you will try to find which of the documents are the most similar, and say maybe you show the top 10 most similar documents, right? So this is the semantic search that I was talking about, right? Just doing an embedding match between the query and the document. Yeah, this is also the same thing. This shows that you have a document, right? Before, and then you index it, you convert it to embeddings, and then you store it in a database, right? And then when you do the query, right, you convert it into embedding, and then you do a nearest neighbor search. I mean, you're trying to find embeddings that are closest to your query, right? So embedding search sounds very amazing, but there are a couple of implications as librarians we should be aware of, right? The pro, of course, is that it can find relevant things even though you don't have the right keyword, right? The main issue, as I'll go through later, is that first, it's a bit of a black box. You make search is very hard to interpret, and it will always find something in most cases. And thirdly, it's non-deterministic. Okay, I'll go through them one by one. Okay, so let me just show you that it works, all right? It works. So if you do, like, for example, it is not raining as a sentence, convert it into embedding. It is sunny, convert it to embedding, and calculate the similarity. You notice that it's 0.18. It's very high, right? It kind of knows that not raining is the same as sunny, right? As compared to it is not raining versus it's raining sentence, the similarity is lower, right? So if you do a typical keyword search, it may decide that the second set of sentences might be closely related because it's matching more words, right? But in this case, this embedding is smart, right? It knows that not raining is the same as sunny, so it gave a very high similarity score. Right? This is just an example to show that semantic search in some ways is superior to pure keyword matching, right? It understands word not raining. There are other experiments, like this is an experiment done by the National Library in Australia. They did it over Trove, which is the Australian newspapers and they did it over a set of newspapers from the 90s, right? And they searched for the word cybersecurity, right? And back then, apparently, cybersecurity wasn't a very common term. And so when you search through the newspapers on the for Australian newspapers in the 90s, on the left-hand side, the keyword search is finding 0 articles. The right-hand side is using an embedding search, and he managed to find newspaper reports about hacking, internet hacking, and so on. So you can see that the embedding search is able to understand that cybersecurity is closely related to internet hacking, right? So you can actually try this link. It actually works, and you can try it on the left, traditional keyword, on the right, embedding type searching, right? The other thing that's a bit particular about embedding search is this. No matter what you put in, right, even you put in rubbish, right, it will find something because what it's doing is trying to find the closest document, right? It's trying to find the closest document. So something must be closest. So in this example, illicit, I entered randomly FHDD, right? I just randomly typed letters on the keyboard, right? In any normal keyword search database, it will say 0 search. But you see illicit, it actually finds like some random documents, even though when you look at it, the words, the letters don't even match, right? But it finds something that's closest, right? So a lot of these semantic search engines, right, be careful, right? They will always return something, okay? Unless they write something to block, like say if the similarity is below a certain score, do not show, right? But most of these tools, they just show regardless of the thing, right? So this is not like a normal keyword search or even like Google Scholar where you put in enough keywords, you get no results. With this style of semantic search engines like illicit, you often get results that makes no sense, right? Even the first result doesn't even match, right? The other thing about embedding search that might frustrate librarians is that it's not very interpretable, right? So like, for example, when you run a keyword search in a database, you can see exactly why a certain result appeared because all the keywords match, right? Or maybe you can figure out that it did some form of stemming. It found a variant of the word, right? Or even the relevancy can make sense, as you'll see later. But when you're talking about embedding search, right, it's using a neural net to learn the numbers. And the numbers may not make sense if you look at them individually, right? So example, you look at Apple, right? You go through an embedding model, you get a set of numbers. You go orange, you get a set of numbers. You get car, you get a set of numbers. Okay, so this is a real example of embedding. I actually did the embedding. I'm using an OpenAI text embedding, a very popular embedding model. It's a 1,536 dimensions. That means, in other words, each word will be represented by 1,536 numbers, right? And you can see apple, orange, and car, right? These are real numbers that pull out. Can you see any pattern? Can you see what the first number represents? Can you see what the second number represents? The answer is you cannot, right? Nobody in the world knows exactly what these numbers actually mean, except that when they seem to test it overall, it seems to find similar things. But there's no human being on the planet who can tell you the first number represents something, the second number represents something. It just works, right? So it's not very interpretable at all, the embeddings, right? Worse yet, right? When you do document matching, it's even worse, right? So when you do keyword document matching, right, if you look at the way it ranks the relevancy, you can kind of make sense, right? So for example, you'll go like, oh, there's this thing called TF-IDF, term frequency inverse document frequency. Okay, some of you may remember this in library school, some of you may not. But the idea is simple, right? So the idea is if your query appears many times in the document, the term frequency is high, and therefore the relevancy must be high, right? And then after that, you must take into account the fact that what word is being matched, right? If the word being matched is a very common word, take an extreme, the word the, right? If the is in every single document in your database, matching the is not important, right? Because every document has it, right? But if it matches a word that appears in maybe only 10 documents, then the relevancy is even higher, right? So the main thing about this is that you're working at the word level, the query word level. You can see the documents matching. But if you look at the semantic search type of thing that we're doing right now, actually what actually happens is that the query and the documents, when they pass through the model, right, you do get embeddings for individual words. But what you do is that you average them together to get one embedding for one document, right? So the whole document is represented by only a series of numbers. You cannot see each of the words. And it's only the document embedding that you do a cosine similarity, right? So you're combining at the document level, and therefore all you get is a number, right? So even if you're an OpenAI expert, engineer, right, why is this result the highest score, right? The only thing you can say is the embeddings, when they did a cosine similarity, the score is higher. There's no way to see inside to see which words are matching, right? There are solutions to this, which I won't go into. Like this is a cobalt where you actually store the embeddings for individual words in the document, and then you do the matching per word, right? So this is slightly more transparent because you can see which of the query words match which of the document words. But this one isn't very common right now because it's extremely expensive to do, because you have to store embeddings for individual words as opposed to the earlier one where you have one embedding per document. Okay. The other thing that people might notice about this type of search is that sometimes the results are non-deterministic. In other words, right, you run the search and then maybe you come back 24 hours later, you run the exact same search, the results are different, right? And it's not because the database changed, right? The results are different, right? So the query, the documents that is maybe ranked differently, right? The top 10 might be different, right? So this is a review in Katrina, which is like a library journal about clinical key AI, and the reviewer noticed that if you try like 48 hours later, the results are somewhat different. Not just a summary, the summary is different, but also the order of the references are different, right? So there are a lot of technical reasons, right? The main one is because it's using approximate nearest neighbor, which means that it may or may not find the closest neighbor, right? So there's some trade-off between speed and accuracy, right? And typically they're going for speed, right? So sometimes you may find, like say, this document is the highest similarity. Sometimes you might find another one, right? The technical reason doesn't really matter, except that you should be aware that such tools, right, they are non-deterministic. That means you run it multiple times with the exact same query, you may or may not get different results, right? This is different from normal keyword. Boolean keyword will always give you the same result, same order. Yeah, so the other thing you'll notice that embedding search is powerful, but it is not but it doesn't mean that keyword search is disappearing, right? Because embedding search has a couple of issues. It's very slow, right? And sometimes you do want to match specific keywords. Like you search for a specific protein or gene, or you search for a specific person name, right? You want to do keyword search, right? Semantic search might give you like similar people, right? And there's a technical reason is that a lot of these embedding models, they are fine-tuned to work well for certain domains, right? So for example, they train the embedding model to be good at understanding, say, law jargon, or good at understanding chemistry jargon. But typically, it means that it'll be lousier at the domains that it's not trained on. So if you train on for chemistry, it'll be amazing at knowing chemistry terms, but be lousy at, say, physics, right? So there's a trade-off, right? So there's this paper you can read yourself that actually did a very interesting study about keyword versus embedding search, right? So it basically found that like certain cases, like if you're looking for a name like John Major, who's a prime minister in the 90s, you want to do keyword searching, right? If you throw a lot of embedding search in, you may find other prime ministers of the UK which are similar, right? But certain type of terms you may want to use semantic search, like train crash, right? Train crash can be expressed in many other textual terms like railway accidents, crashes. So in this case, semantic search might actually find more things, right? Essentially, right, the longer you write the query, the more like you write in a sentence, there's a lot more semantic intent, right? Like for example, you type the fall of John Major, right? So this is the Prime Minister of UK in the 90s, right? The fall of it's kind of poetic and metaphoric, right? It could mean the decline, the ouster, the downfall, right? Or how John Major stepped down, right? All different ways of expressing. If you do keyword search, you just match the fall of, right? Which may not be what is in the document. So semantic search for this is a lot better than you try like a normal keyword searching. Right, and as I mentioned, as I showed you before, right, it can find terms even though the jargon is newer. So, like for example, the earlier example where I searched for cyber security, cyber attack, right? The newspapers would say keyword search would say nothing because it wasn't used in this term. But the embeddings, which were trained on current data, knows that internet type of hacking is a cyber attack, and therefore is able to find it, right? So the short story of it is that because keyword searching and embedding searching or semantic searching have strengths and weaknesses, most of the current systems that do semantic searching combine the two. They run two algorithms or more, right? So an example is, let's say you have a full set of documents, say 1 million documents. They will run first a sparse embedding model. So this is a typical keyword searching, right? And then you run a dense model, which is the embedding search I'm thinking about. Say, take the top 5,000 results for both, right? And then combine them, and then do a further re-ranking, right? So the re-ranker is basically an algorithm that's very powerful at knowing what's relevant, but very slow, right? There are multiple types of re-rankers, but the current technology that's probably one of the best is to just feed the document to something like GPT-4 and ask GPT-4, is it relevant or not, right? Later, I'll show you a tool called Undermine that actually does this, right? So this is very powerful, right? But very expensive and very slow, right? So you cannot say, like, I'm going to take 1 million documents and every single one ask GPT, is it relevant or not? It's way too slow. So typically what you do is that you use a faster model, like a keyword search, a bi-encoder embedding, then narrow down to say the top 10,000 results that are potentially relevant, and then you re-rank them using the most powerful re-ranker you have, which could be GPT-4, for example, right? So how do you actually use such tools, semantic search tools, right? One way to use it is at the very start. So when you're doing a first search, you may not know the right keywords. So this makes semantic search very powerful, right? Like in this example, I said, does making papers free to read increase citations? Of course, you know that there's a technical term called open access citation advantage, right? But if you do not know, you type in natural language, it still finds you relevant papers. And then when you look through these papers, you realize that there's actually a term called open access citation advantage. And you can use this to do keyword, right? So sometimes I do this, right? I'll throw it in a semantic search engine, look at the top 10 results and figure out what keywords I might want to use, right? The other type of use is the other way around, right? You do a very comprehensive keyword searching, and after that, you do a semantic search just to make sure you did not miss out anything. Right? So this is very powerful for so-called search-resistant concepts, things that are very hard to find the keyword for. right? For example, in certain new areas, right, people might be using slightly different terminology because it's not yet settled, right? Then semantic search might be able to find the papers that are relevant, even though they're using different keywords. Right, so this leads to a question. For semantic search type engines like Elicit, CitationBase, and so on, how should I input my query? Right, should I input it in like keyword style? So like open access citation advantage, right? No stop words, you drop everything, right? You just put the main keywords. Or natural language style. Is there an open access citation advantage? The third thing that librarians might try is prompt engineering, right? So some of you may be teaching prompt engineering using ChatGPT, right? So you could type like you are leading expert in open access, right? This is called rule prompting, and then express what you want, right? I won't go into this in detail. I'll talk about this later. But currently, right, the best way to do it is to just do it in natural language. Just type a single sentence, right? Do not try to do prompt engineering, right? First, right, there is a lot of empirical evidence from papers, information review papers, that for this sort of semantic type of search, typing in natural language is better than typing in keywords. Because this type of tools, right, they actually understand meaning, they understand the order of the words, right? So even the stop words help it understand, right? Therefore, for this type of semantic search, type in natural language. And also, I've also asked the machine learning engineers of such products like Elicit and Cite, and they all say yes, type in natural language, right? You can try typing in keywords, it will work, but my own experience is that natural language is superior if you type in natural language, right? And also, if you look at the interface, right, most of the interface will give you examples. They are all typing in single natural language, right? Sometimes it will suggest you actually put a question mark, right? So my suggestion is, as a librarian, do not try to make things complicated, type in natural language. So there are a lot of other issues about such tools. Sometimes semantic search gives you poor results. Let's say you want to match a certain person's name or a certain gene, right? And it keeps coming out related genes, right? A lot of these interfaces like Elicit or CitationBase, there's a feature to like filter down to the particular abstract or keyword, right? So here I'm saying I only want the document to have Lee Kuan Yew, right? So you can force it to do like keyword searching, right? The other thing is that sometimes these tools, right, they tend to give, because what they do is that they tend to find papers that are similar, right? They tend not to weight citations. So they don't care if a paper is highly cited or not, right? So I got a lot of feedback from faculty that they don't like the results that come out because it's not citing the famous papers. So if you want that, a lot of these tools, they now have features to restrict to the top tier journals, right? Typically, they're using something like Simago tier ranking, right? So in CitationBase, there's an option, say only top tier papers. In Cite Assistant, you can even name the journals you want to appear, right? So the other thing that is, I'm running out of time. So the other thing that that we really talked about that's very exciting is called AI. It's called agent-based searching, right? So whether you're using semantic search or textual search, you're only searching once, right? So what we actually know is that if you do iterative searching, that means you do multiple searching, you get better results. So in this example, let's say you use 3 keywords, right? And you found 2 that are relevant, right? The ones in green, right? And then maybe you do citation searching, you found more that are relevant. And then because of the citation searching, you realize that, hey, maybe you should try another keyword search. And you try another keyword search and you find even more relevant, and you continue on and on and on, right? So this is how we normally search, right? So agent-based searching is using the language models like GPT-4 to do the exact same thing, right? And Undermine.ai does this. It's one of the first commercial tools in academic search that does it. It mimics how you search, right? It will do a normal search using semantic or keyword. The other thing about it that's a bit unusual is that it uses the language model like GPT-4 directly to assess, right? So it will look at the top ranked papers and it will send the title abstract to GPT-4 and ask, is it relevant? Or give a score, how relevant it is, right? This is very accurate, right? Very accurate. And there are a lot of studies that basically says that if a human says that a paper is relevant, 9 out of 10 times GPT-4 will agree, right? So you basically have a human reading each title abstract to say, is it relevant or not? Therefore, you can actually type in very, very specific queries, right? But the key thing about this is that it doesn't stop there, right? It will adapt. It will change the keyword. It will do citation searching, right? This is the part that makes Undermine extremely accurate, right? Extremely high quality results, right? This shows like roughly what happens. So it will ask you to type in natural language, but it will actually prompt you to type in detail, right? Because this tool works very well if you're looking for a very specific type of paper. Because GPT-4 is reading the title abstract, you can ask for very specific things, right? So eventually you'll be coached to come up with a very specific question, right? And then you have to wait, right? You have to wait like 3 minutes, 5 minutes, right? Because it's doing multiple searching, right? If you do Google Scholar, it's like 10 seconds. You do Elicit, maybe 20, 30 seconds, right? You do this, it will take at least 3 minutes, basically because it's doing multiple searching. It's doing citation searching and so on, okay? You can't actually see what's actually happening, but eventually when the results come out, you will find that the quality of the results are very good, right? So we actually tried this in SMU, and the feedback was amazing, right? And these are users who have tried things like Elicit, they have tried things like citation-based, they tried AI search tools basically, right? This is the tool that everybody was so enthusiastic about it because the quality of the results are very good, right? So if you use undermine, like for example, one of them found that it would find 90% of a well-studied area, right? So they will have, let's say, a review paper or a survey paper or systematic review. Undermine can find like 90% of it. My colleagues and I are doing more rigorous testing. We are getting a series, like we are not getting 90% all the time. You might find, say, 60% of a systematic review or 80%, right? It depends on the domain and so on and so forth. But essentially, right, the quality of the results are better than Google Scholar or any other AI tool that we have talked about, right? But of course, the trade-off is you have to wait 3 to 5 minutes, which I think is a fair trade-off, right? So agent-based searching is coming, right? So the other thing that, I only have 15 minutes, so I'll go faster. The other major thing that AI search is changing is the fact that it can extract and give you the direct answers to questions, right? So this is an example where I searched who won the FIFA World Cup in 2022, right? So the retrieval augmented generation, retrieval just means search engine, right? So it uses Bing to find web pages with the answer. It will feed the web pages to GPT-4, right, with a prompt, like given the text below, answer the question, who won the FIFA World Cup? And then below will be all the text it has taught, right? And therefore, it can answer the question, and not just answer the question, it can even give you the link to where it found the answer, right? So this is retrieval augmented generation. Very important to understand because all the tools that you're using that gives you an answer with a citation are using a variant of this technique. Okay, this is the most important concept to understand, right? So the fact that it searches to find an answer is very important, right? So this is an example where this is GPT-4o1, right, which is the most powerful model, right? It's a reasoning model, I call it OpenAI, but it does not search. So when I ask it, what are some webinars I'm speaking at in 2024, it totally fails. It doesn't, they don't have any information, right? Because it's not able to search the web for real-time information. If you ask GPT-o1, you ask it like, what's the price of Bitcoin today? It can't answer either, right? Because it can only answer based on its training data, which is usually like 6 months ago or 1 year ago, right? But the moment you add search, right? So it's the GPT-4o, this is a older model, right? But it has search, it can find the answers, right? It can even find the current webinar. I did it yesterday. It found the webinar I'm giving today. And you can even see on the right, where it found the answers, right? But you must turn on the search in ChatGPT, right? So this is retrieval augmented generation, right? It searched, it found relevant documents, and then it asked GPT to answer based on the documents it found, right? So this is retrieval augmented generation, right? And of course, in academic search, it's being done in various things. Like for example, you use it for individual documents. Like this is JSTOR, can check with PDF, ask questions over the PDF. And of course, the more common one is to do it over multiple documents, right? So this is Primo Research Assistant. You search what is the performance of ChatGPT in doing title abstract screening for systematic reviews. It finds the 5 results that might be relevant, and then it generates answer based on the 5 results, right? So this is very common, right? Scopus AI, Web of Science, Research Assistant, Elicit, they all have this feature, right? The thing you have to be careful about is that people will tell you, oh, it doesn't hallucinate, right? Using RAG, it doesn't hallucinate. You have to be very careful. It does not hallucinate in the sense that the documents it found are definitely real. Okay, it's definitely real. The search found the document, but it might still misinterpret the document, right? The technical term is that it does not guarantee 100% citation faithfulness. You look at this answer that I did earlier. What are some webinars Aaron Tate is speaking at? It found this information retrieval meeting 2024, and it gives this link, which is a real link, a real paper, a real web page. The problem is this is not a webinar. This is a face-to-face meeting, right? So I'm not sure how it interpreted this web page. I read this web page. It doesn't say webinar, but but basically it said it thought that this was a webinar and gave this as a webinar. Okay, this is not a webinar. So this is what I mean by retrieval augmented generation does not guarantee that the answer is faithful to the document it's citing, right? This is a very important concept, right? But the good thing is there will always be a citation, and therefore you can always confirm, and you should verify, okay? So there are a lot of studies about it. This is one of the first studies. I love this study, but I won't go into detail. But basically what this study did was that they studied things like Bing Chat, U.com, and a few other very early search engines that use retrieval augmented generation, right? And they found that there were a lot of sentences that were not supported by citations. And the other way around, the citations that were generated may not support the sentence, right? So the best one, for example, right, the best one was Bing Chat at the time. They found that only 68.7% of the generated sentences are supported by citations correctly. And the other way around, whenever it gave a citation, 90% of the time it actually did support the sentence. And the paper goes into great detail about like, oh, you know, if the answer is in a table, it tends to fail because at that time it didn't fully understand how to read tables, right? But the interesting thing is that what they did was that they asked people to actually rate answers, right? Is the answer useful? They call it perceived utility, and whether the answer is fluent. And one stunning thing they found is that there's an inverse correlation between perceived utility of the answer and the citation accuracy. In other words, right, the answers that people said were useful, actually the citations were wrong. That means the citation is not faithful, right? So this is, why is this happening, right? Why are the most useful answers seemingly having the wrong, least faithful citations? The reason is because when the search engine, let's say, is asked a difficult question, and it finds 5 papers which do not answer the question. So what it tends to do is this. Either it will go like, okay, I'll try to use these answers to answer the question, in which case when you read it, it does seem to be useful, it does seem to answer the question, but because the citations don't really answer the question, when you look at the citations, you realize that the answer is not supported by the citations. Or it could be faithful. It could like, okay, I'll generate sentences that do support the citation, but because the citations do not answer the questions, and therefore the generated text will look not useful. So the perceived utility will be low, right? So therefore, there's an irony where a paradox where if the answer seems to be answering the question, you might be very careful to see whether the citations actually say that or not, right? The other paradox is between fluency and accuracy of the citation. This one is quite easy to understand, right? So imagine if you find five documents, right? The safest way is to extract exactly the sentences and throw into the answer, right? Then it will definitely be faithful to the documents, to the citations. But if you do that, they will say it's not very fluent. So what these engines do is that they try to paraphrase, right? So the more you paraphrase, the more fluent the answer seems. But the more you paraphrase, the more likely you will start to be not faithful to the citation, right? So this is a very, very interesting paradox that you should be aware of, right? And this is an academic search engine. It can get things wrong, by the way. I'll just show you, right? So in this case, right, it says that like there is a consensus in the academic community that it should not be used alone in that Google Scholar should not be used for systematic reviews, right? This is true. But I've read a lot of these papers and I instantly spotted this paper. And I know that this paper actually says the opposite, right? If you look at this paper, you look at the conclusion, it says that it could be used alone, right? So why is Google Scholar saying, why is this search academic search AI search saying that this is saying that you cannot use alone, right? The reason is because if you look at, it's actually extracting from the abstract, right? So the abstract says that it is said that should not be used in isolation, right? So it's taking, so it has problems telling the difference between what the paper says about other papers and what the paper itself found out, right? So this paper itself is saying the opposite. It found the opposite, right? But the abstract was talking about what other people are saying, right? Or you can get cases where, less serious cases where there are indirect citations. Like in this case, this is site assistant. It says that Wickman suggests that blended approach for information literacy, blah, blah. So it says that Wickman says this. But if you look at the interface, which allows you to tell you Wickman actually doesn't say that. Wickman is actually citing Arnold Gazos saying that, right? So actually, the correct citation to this is not to Wickman, it's to Arnold Gazer, right? So this is a less serious issue, but still wrong, right? Indirect citation, right? You cite the person who actually said it, right? Which is Arnold, not Wickman. So basically, again, it's the same issue, right? It can't tell when the paper is talking about itself, when it's talking about other studies, right? And there's this very interesting HKUST paper where they actually studied this, and they found that often the answer will be inaccurate because it will be extracting from different parts of the paper, right? Yeah, and I'm pretty much done. Right, this is basically what I mean by creating a synthesis table, right? So you could use undermine to create a table, right? And each row would be a paper, and then columns would be about the paper, right? And this is using retrieval augmented generation. And again, there are a lot of issues with this, so they can be wrong and so on and so forth, right? I'll skip through all this. These are the latest technologies that can actually generate even full Wikipedia articles, not just a short answer. Right? You can try it yourself, right? There are a lot of all these implications we'll skip through. The main thing I want to say is that, again, when you're using a RAG type system, do not type in natural language, right? Prompt engineering, by the way, a lot of the prompt engineering that you are used to was trained on GPT 3.5 and 4, right? So these were language models, chatbots that did not search, right? So do not use the same strategy for prompting GPT and using in this type of AI search tools, right? So do not do that. I'll skip through all this, but essentially when you think about it, it doesn't make sense, right? So there are some prompt engineering techniques that say, oh, if you tell it things like, I'll tip you, you get better results. But the problem is you're doing search now, right? So if you do these things like, I am going to tip 50 for good answers, will be converted into embedding, and then you'll try to match, right? Which is usually not a good idea, right? But the thing is, you won't notice because half the time the semantic search is so good that it will learn to ignore these words, right? But it does not help improve the results. Right, and it's not just me saying it, okay? So you can see officials like Site AI, they're saying that, oh, they already do their own prompt engineering because you remember it creates its own prompt to do the retrieval augmented generation. So if you try your own, may not work as well, right? This is being polite. I think you shouldn't do it at all. You should just type in natural language, right? And as again, follow the examples in the title, right? So I'll skip through the rest. Essentially, it's just saying that be very careful, right? Like here, I'm asking what is some work done on critical thinking, and I'm saying only cite SMU papers. You can actually do that, right? And then it starts to make up things. It says that, oh, there's this paper on bilingualism and on cognitive flexibility, right? But you look at the paper, it never says anything about critical thinking. So it just bridges it and says closely related to critical thinking. Right, so it may not be on critical thinking. In fact, it's not. You read the whole paper, it doesn't say anything about critical thinking, but it just tries because you force it to say you must cite only this set of papers, and therefore it kind of mixes things up a little bit, right? This paper doesn't talk about critical thinking at all, right? And you can actually check to see what it actually says. Yeah. So so basically what I'm trying to say is that this new generation of LLMs is fundamentally different, right? There's a lot of things to think about: natural language inputs, black box. Direct answers have unknown error rates, and then copyright issues, which I'm not even going to touch, right? Because a lot of these tools can allow you to upload PDFs to ask questions. Are you allowed? And then, of course, information literacy, there are a lot of implications, right? So I'm basically done. Are there any questions? Let me see.
And any questions for Aaron Tai?
Yeah, so maybe I'll just answer one of the earlier questions that was sent. So this question about copyright, right? How should we handle copyright or such tools? The thing is, I can happily say I'm not a copyright librarian, so I can't answer. But I think what actually happening right now is that there's a lot of cases in waiting for the courts to decide, right? So it's unclear right now how the courts will decide. So a lot of it would stem on how risk-taking your institution is, right? So I know, like, for example, in SMU, there are a lot of researchers who want to do machine learning and do using GPT models, BERT models to create recommender systems, and they want to do it over, let's say, textbooks, ebooks, or journals that are subscribed by the library, right? And then they worry that will there be copyright implications. So there are all these things going on where librarians will basically have to decide, like, how high their risk appetite is. If they're not even a library, I would say that the institution as a whole must decide, right? So some institutions might be more risk-taking and go like, yeah, you know, I don't think we'll be sued, so go ahead. And then some will be very, very cautious and conservative and say, no, definitely do not allow, and tell people do not allow, right? So this is something that I can't really say it depends on institution. So you have to discuss it with your legal office, with your professors who might want to do such things. And of course, we are also, of course, facing a lot of cases where database owners are coming to the library and asking the library to sign contract terms to say that we do not allow such things. So there are all these things that are going on that I feel that there's no correct answer, right? We have to wait for developments to see how it goes. Yeah.
Thank you. And from the audience, I have one question. I think most of us may be interested in that. What qualifications do you think a librarian should at least have before they could do AI literacy?
Yeah, first, AI literacy is very broad, right? So I don't think I'm an expert on AI literacy, so I can't really answer that question. And I guess even like, so even in my own area, right, studying AI and search, right? So what is the qualification where you can be qualified to teach AI search tools, right? Let's be more specific, even broad. And the answer is like, right now, there is no course, right? And how deep do you want to go into, right? So apparently, obviously, I went into very deep, right? I went to study actually, I had a lot more slides and more detail, right? But at what level do you stop before it goes like, the more you learn, it doesn't help. Right? So actually, I think I reached a point where like I know a lot of technical detail. I can read the archive papers on the cutting-edge information retrieval, but it still doesn't. In most cases, there's no implications for librarians, right? So I think to some extent, right now there is there's no qualification, right? Eventually, people will do it. Maybe I'll start a course certifying on AI search. I don't know, right? But right now it's more about like okay, the other thing, of course, is to learn yourself, right? So I actually have a slide where I showed like the areas where how I actually learn about information retrieval. So for me, for example, I learned from not just peer review papers, because peer review papers are initially very hard to read, right? So I learned from like blogs. So there are industry blogs from people like Vesper, Elasticsearch, right? They write very clearly to explain how all this semantic search and embedded search works, right? So I even attended like online courses on information retrieval 101, com science, right? So I slowly built up some technical knowledge, and then of course I combine it with learning and playing with all these tools like Elicit, right? And sometimes I discuss this with their engineers, and then over time I build up a base of knowledge so that I can say, okay, which parts are useful for librarians to know, right? There's a lot of detail that I could have gone into, but a lot of times there's no implication, right? So at this point, I think there's no certification. Even if you're a com science graduate, right, you may not even know a lot of information retrieval, right? Or you may know a lot of detail, but you're not sure how it applies to what librarians need to know, right? So at this point, it's self-learn. If you want to learn about information retrieval and AI search, I would say the best place to follow is me, follow my blog, because I'm really obsessed on this area. Yeah.
Thank you so much. I believe our audience learn a lot from your presentations, and you share with us that how you can differentiate the features between the different type of AI tools and how to leverage those advantages and avoid the biases and the pitfalls. And after this session, I will share the slides and the recording with all of the registrants. Thank you so much for coming, and thank you, Aaron, for giving us such a wonderful speech.
Thanks for having me.